You ever stop and wonder how our world got, well, so fast? I mean, we've got instant translations, cars that drive themselves. All these incredible things are built on a foundation of just insane computing power. But, how does it actually work? Well, let's dive in and figure it out. No, really, just think about this for a second. To train a really complex AI, you're talking about billions, maybe trillions of calculations. Your average computer, it would literally take years. But these new systems, they're knocking it out in days, sometimes even hours. So, how in the world is that even possible? Well, it really boils down to two things. Just two. You need incredible speed, right? The raw horsepower to crunch all those numbers. But you also need unbreakable safety. You need a guarantee that the whole thing isn't just going to fall over halfway through. And these two ideas, speed and safety, they're pretty much the engine driving our entire modern world. All right, so first up, let's talk about speed. Because to get the kind of performance we need for something like AI, we've got to think way beyond our normal computers. We have to look at a much more specialized kind of hybrid approach. Okay, I think the best way to wrap your head around this is with an analogy. Think of your computer's main processor, the CPU, as a master chef. This person is a genius, right? They can handle any complicated, unique recipe you throw at them, but they do it one step at a time. Now, a GPU, that's completely different. That's like an entire army of line cooks. Each one is specialized in doing just one simple thing, like chopping onions, but they can all do it over and over and over again, all at the exact same time. And that analogy, it perfectly explains the difference in how they're built. You see, a CPU has just a few really powerful, super versatile cores. But a GPU? Oh, it has thousands of simpler cores, each designed for one job and one job only, to tackle a massive number of parallel tasks all at once. But here's the catch. The GPU isn't some magic bullet that's faster at everything. Not at all. If you have a small task, say a simple 16 by 16 matrix calculation, the CPU is actually faster. Why? Because it takes time to package up the job and send it over to the GPU. It's only when you get to these huge, really computationally expensive problems, that's when the GPU's army of cooks just leaves that master chef completely in the dust. So the question is, how do you actually manage this army of cooks? Well, programmers use special frameworks like NVIDIA's CUDA to coordinate the whole thing. And it's a pretty logical workflow when you think about it. The CPU, our master chef, calls the shots. First, it sets aside some memory on the GPU. Then it copies over all the data, our giant pile of onions to be chopped. Then it tells the GPU to go, launching the main computation, or what they call a kernel. And finally, it grabs the finished results back. It's just a super efficient way to hand off the heavy lifting. Okay, so we've got this mind-bending speed. Problem solved, right? Well, what happens when you're 3 days into a massive calculation and some little component just fails? Poof! All that work potentially just gone. And that brings us to our second, equally important pillar, safety. This is where a super important concept called fault tolerance comes into play. The best way to think about it is like a computer's immune system. See, the goal isn't to prevent every single tiny error from ever happening. That's impossible. The goal is to be able to detect when something goes wrong, respond to it, and keep the whole system from having a complete catastrophic meltdown. A total system failure almost never just happens out of the blue. It's a process. It usually starts as a tiny hidden error. Then, if enough of those little errors pile up, they become a detectable fault. And if that fault isn't dealt with, that's when you get a failure. The whole point of fault tolerance is to jump in right there at that fault stage and stop it dead in its tracks before it ever gets to stage 3. So, how do we actually build systems that can survive these kinds of faults? Well, it turns out there are two main strategies that act like a safety net, and each one has its own set of pros and cons. All right, the first strategy is called replication, and you can think of this one like having a stunt double for your system. It's an exact copy, running in parallel, ready to take over instantly if the main system goes down. The second strategy is checkpointing. This one is way more like saving your progress in a video game. Every so often, the system just pauses what it's doing to save a snapshot of its current state. Now, these two strategies present a really clear trade-off. Replication, the stunt double, gives you the absolute highest reliability and instant recovery. But it's super expensive because you're literally running and paying for two systems at once. Checkpointing, on the other hand, is way cheaper on resources. The downside, recovery takes longer because you have to go back and load up your last save game. So the whole trick is picking the right strategy for the job at hand. And the checkpointing process itself, it's really as simple as it sounds, just like saving that game. The system does its work for a bit, then it pauses, saves a complete snapshot of everything to a safe place, and then it just gets right back to it. That way, if a failure ever happens, no big deal. It just loads up that last snapshot and carries on like nothing happened. So, okay, let's bring this all home. On one hand, we have this incredible parallel processing power that gives us amazing speed. And on the other hand, we have these really robust safety nets that give us resilience. It's a combination of those two things that truly powers, well, everything in our digital world. You see, modern systems don't just pick one or the other. They use a smart hybrid approach. The CPU acts as the master chef, the brains of the whole operation, handling all the logic and the step-by-step tasks. But whenever a huge parallel job comes along, it offloads it to the army of cooks, the GPU. At the end of the day, it's all about sending the right task to the right tool. And you might be thinking, okay, but why does this actually matter to me? Well, think about something as simple as an ATM. It needs a ton of computing power to process thousands of transactions. But what's even more important is that it absolutely, positively has to be available 24/7. And how do they do that? With fault tolerance, probably replication, ensuring that even if one server goes down, the service never stops. And that right there is really the key takeaway from all of this. Building the modern world we live in isn't just about raw power or making things go faster. It's about engineering smart systems that combine that incredible speed with the toughness, the resilience, to handle all the inevitable glitches and failures that are going to happen along the way. Which kind of leaves us with one last big question to chew on. As our world becomes more and more dependent on these automated, super high-performance systems for everything from our money to our health, are we really putting enough effort into making sure our safety nets are strong enough? Are we making them not just fast, but truly fundamentally safe? It's something to think about. Thanks so much for joining me.